let's discuss a very high-level topic, the abstract data type. Now I'll get to that term in a minute, but I'm going to start by drawing a distinction between the interfaces we've seen so far and the implementations. We saw that in class, for example, that we can have an interface called list61b with many possible implementations, say A-list or S-list. And each of these has a really different idea of how that list should be implemented. This is based on arrays, in particular resizing arrays, and S-list was based on a linked list. We could also have a D-list, a doubly linked list, and many other things you might imagine. In the projects, what you did is you created a deck interface, and then created an array and a linked list-based deck. And just as before with the list61b, there are so many other possibilities. We also saw in one of the most recent lectures that the disjoint sets interface, that there's so many different possibilities here, a very rich set of things that one might consider. We started from the list of sets, the disjoint sets implementation, worked our way to weighted quick union, and then eventually also added path compression, not pictured for lack of space. So this is a really important thing to realize, is that an implementation is a distinct thing from the more abstract data type that we have up here, say disjoint sets. And so that brings us to the term abstract data type. So we'll say that an abstract data type is a type in a programming language that is defined only by its operations and not by its implementation. So the deck abstract data type consists of all of these methods here. And we can have many different implementations. So to go to our old friend, the allegory of the cave, you can think of the abstract data type as what the cave dwellers see, and you, the monks who are running the world from behind the scenes, you have many ways you can achieve the objective of tricking the people into the cave into seeing the behavior that they want to see. Okay, so to give you a sense of the trade-offs that come up when we look at abstract data types, let's consider a couple of new ones you've probably never seen. Well, you might have seen stacks before. So the stack abstract data type, it supports two operations. It has push and has pop. So I have here a stack which currently contains the number 4, and if I push the number 6, it appears on top. If I then push the number 2, it appears on top. Now, if I call pop, well, because of the nature of the stack, it's going to come off the top. Why? Because that is the abstract data type. Those are its operations. We define semantics for them. That's all it does. So when we pop, 2 goes away and it gets returned. If we pop again, 6 goes away and it gets returned. And those are the operations that our stack provides. So my question for you now is, what specific implementation do you think would be better to support the stack abstract data type? If we now want to produce that behavior using one of our two tricks, linked lists or arrays, what would we want to do? Okay. So it turns out that this problem was a bit of a trick question. Actually, both are pretty good. So you can imagine that if you use a linked list, well, then you're just going to have to maintain a singly linked list, and it's pretty easy to implement this. It's almost like the deck that you did in the project, except simpler, because you only have to worry about pushing and popping from one end. Same deal with the array. If we use a resizing array, then we just build an array, it gets bigger, we resize when needed, and when we pop, we just take the last item and then resize down if necessary. So both will be about the same, though I would argue in this case that linked lists, there's no resizing, so it'll be a little bit faster. But actually, both of them are equally good. And you could do this, if you want, you could do a detailed mathematical analysis and show that they both have average constant time operations. So even though arrays have some resizing, still works out pretty well. But I guess if you really wanted to give an answer, linked list is slightly better, but I'm okay with either. All right, another one, the grab bag abstract data type. So the grab bag has 4 methods, or 4 operations. It has an insert operation where you put an item in the grab bag. You have remove, where you get back some item at random from the bag and it's gone. There's sample, where you get to peek inside the bag and see one item, but it doesn't go away. And then you can ask for size. So now again, I want you to think about which one do you think would result in faster overall performance for these operations. So pause the video and think about that. Okay, so for this one, it turns out that if we want to remove a random item from the bag, it will be much faster if we use an array-based solution. In particular, if we wanted to, and this is a little tricky, if we wanted to remove, say, an item from the middle, then we could swap the last item with the one we're removing, and then decrement size. And so now the item has been removed, and that took constant time. By contrast, if we had a linked list, then we would have to grab an item, we'd have to go to some random place in the list and then remove it, and that would require linear time in order to find a random item. So this approach, in this particular case, the array is a strictly better solution for this abstract data type. And these questions are very challenging quite often. I mean, this one, I didn't really go into it in great detail. Like, you might not have fully followed how the array removed my work, and that's fine. But I just want to raise the point that these problems can be quite challenging, but they're very, very important. They're a microcosm of the kind of problem solving you're going to do in the real world, where you're faced with a problem with many different challenges, and these little elemental problems, they help train your mind. So now that we have a sense of what different abstract data types might look like, other than the ones we've already seen before, I will tell you about some important ones in Java. So in Java, as you guys have seen before, we can do lines of code like this, where we tap into the java.util library and say, I would like a list of integers, and in particular, I would like a new array list. Now, one thing that's so cool to me, as somebody who is intellectually excited somehow about the difference between abstract data types and concrete implementations, is that Java syntax allows you to write that right in your code. This is just some list, but we're not saying what kind. It's abstract. And we're saying, well, specifically we want an array list, but really the variable in this case is a list. Oh, you know what we didn't do? Give it a name. All right, there we go. Now it has a name. Now, I should note that interfaces in Java are not purely abstract, because they can contain some implementation details. That is, we can have default methods. Now, some of the most important abstract data types that Java has available to us in the form of interfaces are the list, the set, and the map interfaces. These are very famous. They are collections that they're interfaces that each extend the collection interface. So this represents lists of things, this is sets of things, and lastly we have map, which is mappings between items. So that would be, I mean, you've seen maps before, but just as a reminder, it would be like JHug's grade is 88.4, or Creature C's north neighbor is a plip. Now, maps are also known as associative arrays, associative lists, symbol tables, dictionaries, and there's actually other terms that are used, but those are some of the most common. So to give you a sense of why a map might be useful in a specific task, let's say we want to count the number of times that the words number of times that each word occurs in a string. So I have here sumomomo, right? Sumomo mo momo mo momo no uchi. All right, so this right here, I want to count the words, and to do this, I create a map that goes from strings to integers, and in this case, one of the specific implementations, which we'll be talking about in this lecture, is the tree map. So I will say for each string in the text, I'm going to get the current count of that word in my map. So I'll say m.get the current count of, say, sumomo. And then if that word does not occur in my dictionary yet, then I'm going to return 0 instead. So this is my default value. And then I will put, that is associate with the string, the current count plus 1. Or if you know Python, I've put it down here so you have a piece of code you can compare to. And when you complete this code, you see this nice map that says sumomo appears 1 time, mo 2, momo 2, no 1, uchi 1. So the built-in package, a Java util package, it gives you a lot of useful things that you can use, as I said, lists, sets, maps, and different implementations for each. And so what we will do in this lecture is see how sets and maps can be implemented using the tree set and tree map approach. And what's kind of cool here is we've already seen how we can implement a set in a previous lecture when we did array set. We're going to do something new, totally new. It's not arrays, it's not linked lists, it's a new thing. And that'll get us our tree set and tree map implementation. And it'll be fun.